This video is going to walk you through the various exponent properties that we use in algebra. The first property says for any positive integers m and n, a to the m times a to the nth equals a to the m plus n. Basically what we're saying is that if you're multiplying two exponential expressions with the same base, you can keep the base and add the exponents. It is important to note that you have to have a same base in order for this property to work. I want to kind of show you why this property works. If we have the problem 2 to the third times 2 to the fourth, well, by definition, 2 to the third would be 2 times 2 times 2, and we want to multiply that by 2 to the fourth. Well, again, by definition, 2 to the fourth would be 2 times 2 times 2 times 2. So hopefully you realize we have a repeated multiplication with the value of 2, and there are actually 7 of them. So we could write that in exponential notation as 2 to the 7th. And if you'll notice, that is the same as 2 to the 3 plus 4 if you add the original exponents. So really the properties are based on the definition of exponents. Property number 2 is what we call the power to a power rule. If you have a base raised to an exponent, which is then raised to another exponent, the way you simplify that is by multiplying the exponents. Again, if you go back and think about the exponent properties, 4 to the third squared would be 4 to the third times 4 to the third. And then in each case, you would have 4 times 4 times 4 multiplied by 4 times 4 times 4, which again is a repeated multiplication of 4, and hopefully you can see that that would be 4 to the 6th, which again corresponds to 4, 3 times 2, which are the original two exponents. So when you have a power to a power, you multiply, keep the base, and multiply the exponents. This property is used also if you have multiple pieces or a product within the parentheses. You have to basically distribute the power to each value in the parentheses. So when you look at our example, 7x quantity raised to the third power, again, remember that that 7 has that understood 1 and the x has the understood 1 exponent. And again, if you think about the definition, that would give us 7 times x times 7 times x times 7 times x. So we have a string of multiplications for 7 as well as for the x. And if you notice, there are 3 7s. So it's 7 to the third. And then there are 3 x's, so it's x to the third. So again, if you go back and you think about that, you would have 7, 1 times 3, again distributing the 3, and then x to the 1 times 3. So you do get 7 to the third, x to the third. 7 to the third could be multiplied out, which is 343 x to the third power. So again, all these properties are related to the definition of exponents. The same thing is true if you have a quotient. If you have a quotient and it's raised to a power, again, you have to distribute that power to both the numerator and the denominator. So if we have 4/9 to the third, again, basically we've got to distribute the 3 to the numerator and the denominator so that it becomes 4 to the third, 9 to the third, and then we can simplify that. 4 to the third is 64. 9 to the third is 729. Okay, so again, it's the idea of distributing it to all the pieces within the parentheses. The next property, property number 5, says if you have a division problem and you're dividing with the same base, again, notice you have to have the same base, that when you're dividing, you subtract the exponents. So with multiplication, we added the exponents. With division, we're going to subtract the exponents. Again, if you go back to the definitions of an exponent, again, think about this. You would have 3 to the 7th, so you're going to have 3 times itself 7 times. 3, 5, 6, 7. 3 to the 5th, you're going to have 3 times itself 5 times. And we know when we have the same value in the numerator and the denominator, they will divide out. So we can actually divide out 1, 2, 3, 4, 5. So if you think about the idea that you're canceling them off, dividing them out, you're taking them away, notice that we're left with 3 to the 2nd, or 2 3's in the numerator. So we have 3 to the 2nd, which would correspond to 3, 7 minus 5. Okay, which ultimately is a value of 9. We always like to try to simplify if we can. It doesn't make sense mathematically to have a negative exponent. So if we have one, we have to force it, in a sense, to become positive. And the way you eliminate a negative exponent is you flip it over or use the reciprocal. I like to think about moving it upstairs or downstairs. If it's in the numerator, we're going to move it to the denominator. If it's in the denominator, we're going to move it to the numerator. It's kind of like a flip-flop. So if I have 1 over 6 squared, if I have 6 to the negative 2, and remember that's really over an understood 1, when I flip it, it becomes 1 over 6 to the positive 2. When you do the reciprocal, it becomes a positive exponent. And then we do know that that simplifies to 1/36. Finally, the last property is one of those properties in mathematics that you just got to accept that's the way it is. And that is that any base to the 0 power is always and forever 1. Any base to the 0 power is always and forever 1. Whether you have a positive number like 5 to the 0, its value is going to be 1. Or if you have a negative value like negative 2 to the 0, that's going to be 1. It could be a decimal like 3/10 to the 0 power. That's still 1. A fraction such as 1/4 to the 0 power. That's still 1. Any base to the 0 power is 1. What we do then is we take all of these properties together and we use them to simplify expressions that involve exponents. When we talk about an exponential expression being simplified, it has to meet 4 criteria, meaning each base occurs only once, no parentheses remain in the final answer, there are no powers to powers, and there are no negative or 0 exponents in the final answer. So once you've met all 4 of those criteria, you know that you have your exponential expression simplified into the lowest terms possible. So I want us to take a look at a couple of quick examples using these properties. Our first example is 3x to the negative 4, y, z to the negative 7, times the quantity 3x raised to the negative 3 exponent. Now, there's a variety of ways you can actually begin as you think about working this problem. The first thing I'm going to do is maybe deal with this negative 3. If we think about order of operations, we should do exponents first. So I'm going to deal with that particular exponent so that I have 3x to the negative 4, y, z to the negative 7, and then I'm going to have 3 to the negative 3, x to the negative 3, using the property that says I have to distribute the exponent to all the pieces inside. Then I notice that I have a multiplication problem, and I have the same bases in several places. I have 3 and 3, they're same bases, and then x and x. And since I'm multiplying with the same bases, the rule says we should add the exponents. So I'm going to have 3 to the 1 plus negative 3, x to the negative 4 plus negative 3. The y tags along, and the z to the negative 7 also tags along. It doesn't disappear. It's still part of the problem. It just doesn't have a partner. Then we come back and let's see if we can simplify this. So we would have 3 to the negative 2, x to the negative 7, y, z to the negative 7. Finally, in the last step, I need to deal with all of the negative exponents. Since they're kind of like in a numerator, because remember, this whole expression is over 1, I need to move them down in order to make them positive. So I'm going to move 3 squared to the denominator, x to the 7th, and notice how my exponents become positive, and z to the 7th. The y has a positive exponent, so it stays in the numerator. So in my final answer, I'm going to have y divided by 3 squared is 9, x to the 7th, z to the 7th. And that would be your final answer. Notice I have no base occurring more than once, no parentheses, no negative exponents, and no powers to powers, and no zero exponents. All right, let's look at one more. So I have x to the 4th, y to the 5th, z to the 6th, divided by x to the negative 4, y to the negative 5, z to the negative 6, all raised to the negative 4 power. Again, I want to think about initially dealing with this exponent of negative 4. Again, thinking about order of operations. So I need to distribute the negative 4 to everything on the inside. So I'm going to have x to the 4 times negative 4 using the power to a power rule, y 5 times negative 4, z 6 times negative 4 in the numerator. In my denominator, I would have x negative 4 times negative 4, y to the negative 5 times negative 4, z to the negative 6 times negative 4. And then I'm going to simplify each of those. I'm going to perform the multiplication. Some of you may be pretty adept and can do the multiplications as you go. That's fine. So we have x to the negative 16, y to the negative 20, and z to the negative 24. In the denominator, I have x to the 16, y to the 20th, and z to the 24th. I have x's in the numerator and denominator, as well as y's and z's. So since it's division, we then use the rule that says you subtract the exponents. So I'm going to have x to the negative 16 minus 16, y to the negative 20 minus 20, z to the negative 24 minus 24, which gives me x to the negative 32, y to the negative 40, and z to the negative 48. Can't have the negative exponents, so the next thing that I have to do is get rid of those negative exponents. Again, remember that this expression is over 1, and to make them positive exponents, I need to move them to the denominator. So I'm going to have 1 over x to the 32nd, y to the 40th, z to the 48th. Again, notice in the final answer, I do not have any base that occurs more than once. I have no parentheses. I have no negative exponents, no zero, or no zero exponents either. Okay, so your final answer is 1 over x to the 32nd, y to the 40th, and z to the 48th. This concludes the video on how to use exponent properties to simplify exponential expressions.